Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. In a previous show, I posed the question to you as to what made the Hulk the Hulk. We found out that it's gamma rays, the most powerful form of energy known to exist so far in nature. We also found out that cosmic rays come from gamma rays, and no one knows where cosmic rays come from. My astrophysics doctoral research involves both. Picking up where we left off, I have data to show you. Data that I gathered last month from the youngest supernova remnant in our Milky Way galaxy, categorized as G1.9 plus 0.3, the youngest at 150 to 220 years old. Prior to that, the youngest supernova remnant was Cassiopeia at 320 to 350 years old. But before I do, let's review, and that rhymes. Shall we? Yes, let's.
Has anybody here ever seen the movie Predator? Good movie from the 80s. The alien wore a helmet which allowed it to see in different wavelengths of light: optical, X-ray, infrared, ultraviolet. We may not have a helmet like the Predator, but we do have ground-based telescopes and space telescopes orbiting high above the Earth's obscuring atmosphere, which do allow us to look into outer space with different eyes that enable us to see in the different wavelengths of light. The visible range in which we see is a small part of the electromagnetic spectrum. Just as a group of 6 runners clasping arms will break apart when running from the beach into the ocean, a beam of light breaks up into the 6 major colors of red, orange, yellow, green, blue, and violet, because these colors travel at different velocities when traveling from one medium into another. A new image from NASA's Fermi Space Telescope shows gamma rays, the highest energy form of light, filling faraway bubbles of hot gas created by massive stars. The bubbles are located about 4,500 light years away in a star-forming region of the constellation Cygnus, the Swan, also dubbed Cygnus X. The outflow from Cygnus X's gigantic stars also creates intense magnetic fields within the bubbles. And it is these magnetic fields that help spawn the gamma rays by trapping and deflecting fast-moving particles called cosmic rays. Cosmic rays are tiny electrically charged particles that move at nearly the speed of light. They are primarily protons, and most were probably accelerated to their incredible speeds by star explosions known as supernovas. When cosmic rays collide with interstellar gas or photons of starlight, they give off gamma rays. Here on Earth, we have particle accelerators that can produce high-energy protons. The largest in the United States is the Fermilab Tevatron, with a circumference of 6.86 kilometers, capable of producing protons with energies of 1 trillion electron volts, TeV. The largest in the world is the CERN Large Hadron Collider, LHC, with a circumference of 27 kilometers, capable of producing protons with energies of 13 trillion electron volts. However, cosmic ray protons reach us with energies thousands of times greater. This is data from the Galileo space probe. This is a view of the plasma sphere surrounding Jupiter that we obtained through the eyes of the plasma wave instrument on board the probe. The colors represent energy levels, and this data shows the change in energy as time goes by. A long time ago, in a galaxy far, far away, I was in the Boy Scouts. We went camping far away from the city lights, and I remember looking up at the Milky Way. It really did look like milk had been spilled across the night sky. I did not know it then, but I was looking along the galactic plane towards the center of our Milky Way galaxy. This is a view of the galactic plane of our Milky Way galaxy in the optical range of the electromagnetic spectrum. These are views of our galactic plane in the radio, microwave, infrared, ultraviolet, X-ray, and gamma ray wavelengths of the electromagnetic spectrum. This is data from my research using the eyes of the Fermi Gamma Ray Space Telescope. Our galactic plane is divided into 86 regions to detect as yet undiscovered gamma ray sources. Software programs are used to analyze and model the data. Here are indicated two hotspots, locations of potential new gamma ray sources. Cosmic rays are high-energy protons, ions, and electrons that astrophysicists believe are produced when a star explodes into a supernova. As the shock wave from the explosion expands out into space, it encounters protons, ions, and electrons. Its magnetic field pushes them up to very high speeds, and they gain energy by repeatedly crossing the shock. The process, called diffusive shock acceleration, or DSA, is thought to be facilitated by scattering off magnetic turbulences downstream and irregularities upstream. Charged particles change trajectories when they encounter a magnetic field, making it impossible to directly determine where cosmic rays come from. The source of gamma rays are traceable because photons have no charge and are unaffected by a magnetic field. Cosmic rays can reach energies up to 10 to the 21st electron volts, and below 10 to the 15th electron volts are thought to be of galactic origin. The most promising sources of galactic cosmic rays are supernova remnants, or SNRs. They are not only energetically favorable, but also provide a mechanism to accelerate particles to very high energies. An important window of observations in the range from 100 mega to 300 giga electron volts has been opened with the launch of the Fermi Observatory. Much of the gamma ray emission can be explained by Bremsstrahlung emission and inverse Compton scattering. However, the model cannot fit a distinct feature at giga electron volt energies, which can be accounted for by adding a pion component to the model, providing evidence for cosmic ray production. Despite all the findings that link SNRs with high-energy electrons, direct evidence for the acceleration of ions by these objects is still lacking. In order to find a signature for proton acceleration, studying the photon spectrum of the sources at gamma-ray energies becomes fundamental. It is expected that a fraction of the high-energy emission would be caused by the decay of neutral pions produced through collisions of accelerated protons with cold ambient protons and ions. If the astrophysicists can prove that the accelerated protons are producing the gamma rays, then the mystery of cosmic rays will be solved.
As I continue with my astrophysics research, I want you to feel like you're right here with me as we do the research, delving into the unknown. Just as much as talking about and demonstrating astrophysics in my research, I want to show you that you can also do astrophysics research. So fortunate for us, there are now dedicated websites from the space telescopes that contain the data that you can access and do your own research. The Hubble Space Telescope that observes in the optical range. The Fermi Gamma Ray Space Telescope that observes in the gamma ray range. And the new Webb Space Telescope that observes in the infrared. They all have websites that contain the data they've collected. Now, the Webb telescope, a small amount of the data is proprietary, which means the research group that collected that data from the Webb Space Telescope has 1 year to analyze that data and to publish it. But after that 1 year, it's open to the public. The data from the Fermi Gamma Ray Space Telescope is available immediately. Data that was collected today is available. What you need to do your own research is a computer powerful enough. And you have to learn the software tools to analyze the data. In astrophysics research, especially with respect to gamma ray research, 32 gigabytes of RAM will pretty much do it. 1 terabyte of storage to start with. And you have to have Linux installed on your computer. Linux is what's used to analyze the data. And then you're good to go. Okay, so what I'm going to do now, I'm going to show you some recent data that I got from home with my desktop computer that was built for me. First desktop computer I've ever had. I've only had laptops up to now. My most powerful computer up to now was an 8 gigabyte laptop. This desktop, 32 gigabytes. Oh, right on. What we're doing here is we are logging into my Linux Fermi data area where all of my files have been generated. You can see there's quite a bit. Now, what I'm going to do is I'm going to bring up what's called the counts map, the source model map, and the residuals map. What that is here's the counts map. This is from the data, from the files that you see in the background. These are the counts of photons from the supernova remnant G1.9 plus 0.3, the youngest supernova remnant in the galaxy at about 100 to 220 years old, younger than Cassiopeia. Now we're going through the different colors of the electromagnetic spectrum, the different energies to show these counts in the different spectrum. Pretty cool, huh? Okay, and again, these are the number of photons per second per square meter for a certain energy from this supernova remnant. Now I'm going to bring up the model map. Okay, this uses the bin likelihood to calculate the probability, given the data that the counts map shows, that if you maximize the spectrum, you'll get an ideal counts map. And this is called the source model map. And again, we're looking at it through the different ranges of the electromagnetic spectrum. Okay, number of photons per square centimeter per second per energy. Okay, now what we do is we subtract the actual counts map, the first one that I showed you, from the model map to see how close they compare. And the closer they are that they match, the better the data is that we've been able to model it. So now what we're going to do, we're going to bring up the residuals map. And I'm going to do the same thing. I'm going to enlarge it and then take it through the different ranges of the electromagnetic spectrum, the different colors. So here's the residual map. And now we go through what we did for the counts map and the model map. You can see this residual map is not too bad. I mean, it's pretty close. Okay, so this gives you an idea of how we're going to be analyzing the data as I go through my research. We're going to do side by side. Okie dokie. Oh, before I stop, let's get all three up at the same time so we can really compare. What do you say, huh? Okay, let's do that. Oh, there we go. Got them all. The counts map, the model map, and the residual map all together. Okay, so now we shall continue. And remember, FAT, spelled P-H-A-T, physics with attitude. Enjoying physics as the window into our amazing world of nature, and mathematics as the tool to open that window. So as we continue into our research, delving into the unknown, tune in next week. Same fat time, same fat channel. Okie dokie.